afternoon, everybody. Oh, almost there, almost at the end. Good afternoon, everybody. Try it again. Much better. How's build going? Yeah, well, it's hard to see. So, looks like there's a few people in here. It's nice to see the interest in blockchain. My name is Mark Russinovich. I'm the CTO of Azure. And this session is an introduction to blockchain and cryptocurrencies and smart contracts. How many people have invested already in Bitcoin or another cryptocurrency, just out of curiosity? Yeah. How many people are here just because they want to get rich? For those of you watching, that was everybody. Raise their hands. So what I've got is a session here where I'm going to cover the background of this whole Bitcoin, cryptocurrency, blockchain craze that's going on, and take you inside some of the technical details, behind the technology, behind just the headlines that you're seeing. I'll start with an overview of Bitcoin mania for those of you that maybe haven't been paying attention and were living under a rock for the last year or so. I'll give you an overview of what's been going on with respect to Bitcoin, especially, and other cryptocurrencies. Then I'm going to talk about where Bitcoin came from, its origins, and some of the theories around how it emerged. I'll talk then about blockchain basics, and this is where I'm going to get into some cryptography, just a very basic level. Some of you already might be familiar with it, but I'm going to cover the fundamentals of some of the public key cryptography that's really behind what blockchains are made of. And I'll take you inside then what a blockchain actually consists of underneath the hood. Then I'm going to explore some of the other blockchain networks besides Bitcoin and some of the other uses of those networks, specifically the use of smart contracts, which are transactions on the blockchain that can actually be executed. I'll talk about the limitations of blockchain, some of them with respect to the current technologies that are deployed, and dive in a little bit into what we're doing to try to help enterprises overcome those limitations with the current technologies out there. And then finally, I'll just give you, for those of you that do want to get rich, a little guide on how to get started with blockchain. So this is what you've probably been seeing. It's an article headline from the New York Times. Everybody else is getting rich and you're not because you don't own Bitcoin. And you probably heard your neighbors talk about it, your kids talk about it. I mean, I've got friends that their kids basically are saying that they're going to retire because they're making all this money off cryptocurrency, so they don't need to go to college. And so this is really causing this is a new word I've learned, FOMO. This is causing this FOMO effect. Anybody know what FOMO is? Yeah, so the millennials in the house there. It's a fear of missing out. That's what this is causing. And you're seeing stories like this that it's contributing to it. This is one from Seattle just a couple months ago where somebody actually went and bought a house, at least that's the headline, in Tukwila, using Bitcoin. And actually this is an example of the press kind of stretching the truth to get some attention. This person didn't actually buy their house with Bitcoin. They put the down payment on their house with proceeds they'd gotten from the sale of some Bitcoin that they'd had. So not quite the way that, and then you saw this kind of stuff. This is just crazy stuff. Companies that would put the word blockchain into their name and then their shares would just go up. And this is one example. This is a company that was working on bioinformatics in the UK. They changed their name, put blockchain in it, repivoted. That's pivoted, the Silicon Valley word for I'm failing, so I'm going to do something different. And their stock went up. And then this one, Long Island Iced Tea, this is a popular consumer drink maker. They're doing decently in the tea business, but then they said, hey, you know what, we can change our name, and then we'll do a lot better. And so their shares went up 200% when they changed their name to Long Blockchain. And so now they're putting iced tea on a blockchain. But if you take a look at what's happened, we're in kind of a small market correction when it comes to cryptocurrencies like Bitcoin. This is since May of last year, and you can see the price there, $5,000, $10,000, $15,000, $20,000. It went to just above $20,000 right around the holiday period, and then you see that it's had a correction, and as of today, it's somewhere at $9,000, $9,100 Bitcoin. So a little bit of a correction, but still, if you invested a while ago, more than a year ago, you're actually in pretty good shape with a Bitcoin investment. And this kind of burst bubble, you're starting to see these kinds of headlines. Bitcoin hype vanishes just like that. We're in the boring phase now. Actually, I don't hear my friends' kids talking about Bitcoin so much anymore because I think they probably bought in right around the holidays when they were off from school. And then you see this, people that really are bearish about the future of Bitcoin and other cryptocurrencies. This is just from a few days ago, Warren Buffett. And I'd never thought I'd hear the words rat poison squared come out of Warren Buffett's mouth. But there it is, his view on Bitcoin. And Bill Gates said he would short Bitcoin. He just said this yesterday. He would short Bitcoin if he could. And turns out you actually can. There's a futures market for Bitcoin. So I sent him an email last night. This is me. I started to play with Bitcoin last year and Ethereum, and I purchased a little bit. And this is from my account as of yesterday. You can see that I spent enough to play with it, $50, and that's what it's worth yesterday, $3,200. So that, just to put that into context, that's almost enough for a new iPhone. And the thing is, I'm killing myself. Like, when the prices started to go up, I'm like, oh, why didn't I just put in 1,000? Because that would have been $1 million at this point. So I missed out. But let's get to the history of Bitcoin. Bitcoin was created or launched as a paper back in 2008. And this, you see the title of this paper, it's academic paper, Bitcoin, a peer-to-peer electronic cash system. It actually has no references, no academic references. So it's written like an academic paper, but not treated like, it didn't treat it like an academic paper referencing other sources as foundation for this work. But this paper, if you're going to read one thing about Bitcoin to understand the way it works, you should read this paper because it's very clearly written. It's very succinct, and really it's what I'm going to be talking about for the next 40 minutes or so. Most of the bulk of the middle of the talk is just what's in this paper. You can see that the author, Satoshi Nakamoto, nobody really knows who this guy is. In fact, nobody knows if it's a single person or an organization. Some people speculate it's the NSA. Some people speculate it's some other mysterious organization or somebody that's just a hermit and just said, here's the technology for the world. But you can see whoever it is, because they gave themselves a bunch of Bitcoin at the start, whoever it is, they're incredibly rich right now. The market capitalization of Bitcoin is $150 billion as of today. And so quite a lot of money. Now, there's tons of speculation about who Satoshi Nakamoto is. And somebody from SpaceX published a blog post at the end of last year saying, I figured out who it is. It has to be Elon Musk. And they provided all this evidence that lines up to Elon Musk as the kind of person that would have done this and then not taking credit for it. And that's why he's so rich. No, that's not the reason he's so rich. But Elon Musk responded to this. I don't have that response here. But Elon Musk responded and said, I am not Satoshi Nakamoto. In fact, he said, I've never bought Bitcoin. Somebody sent me Bitcoin once, and I've lost it. So, and now I'm really sad because imagine how much richer I would be if I'd held on to it. He didn't say that, but nobody knows. But let's talk about the difference between these cryptocurrencies like Bitcoin and traditional currencies like the dollars or whatever foreign currency you might be carrying around with you. That kind of currency is called fiat currency. It's one that's issued by an organization that backs it, and they stand behind it. Now, one of the challenges with fiat currency, especially when you're transferring large amounts of money from one entity to another one, is that there's long delays between the transaction itself and the settlement of the transaction. This period in between where the money is neither here nor there. And if you do a wire transfer, you're familiar with this, it's 2 or 3 days for the wire transfer to clear from one bank, making sure that everything's lined up, and then the other bank making sure everything's lined up, and then accepting the payment and saying, okay, we've got it now. In addition, most of the time, even for things like wire transfers, there's intermediaries involved, especially for large transactions or transactions across country borders. There's organizations like SWIFT, which sit there in the middle and help with the validation of the transaction. Other organizations that sit and will back up the transaction in the case where the Whoever's paying the transaction fee defaults on that transaction amount. They cover it, so there's insurance, there's fees. They're the ones validating it, so you can kind of trust the central authority to say everything looks good before you accept the transaction's amount and start to use it. And that adds a bunch of fees to the transaction. It also introduces additional delays. And because the money is neither here nor there for some period of time, and you have middlemen in the middle, this offers lots of opportunities for fraud. Fraud and loss, like money actually can get lost. And so these are some of the big challenges with fiat currency. Now, cryptocurrency comes along and tries to address these challenges. It's a distributed, decentralized currency. So there's no central authority. Nobody's issuing this money. Somebody creates the cryptocurrency. They specify how the currency gets generated. I'll talk about that later. But once the cryptocurrency is off and running, nobody's in control of it. It's really everybody's contributing as part of a network. There's no transaction settlement clearing. You send a payment from one account on the cryptocurrency network to another one. It's immediately, once the transaction is accepted by the network, it's instantaneous settlement. And there's no intermediaries involved. Like I said, send money from one current account to another one. It's there as soon as the transaction commits. Another very interesting property of these cryptocurrencies is it's got an immutable history of every single transaction going back to the beginning of time or the genesis of the cryptocurrency. And what this means is that it's possible to go track when you get some currency, a Bitcoin, you can go back and track its lineage all the way back to the beginning of time, or all the way back to when it was generated or mined, which I'll talk about. So this has made it very interesting or very attractive for people that believe in no fiat currencies and want to overcome all these limitations. Now, if you go read Satoshi's paper, Bitcoin is built on a technology called blockchain, hence the title introduction to blockchains. And blockchains, you'll hear them also referred to as distributed ledger technology, or DLTs. And if you think about what a database is, one that's keeping track of assets, for example, payments, funds from one account moving to another account, it's effectively the digital version of the old ledgers that kept track of who has what in each account. So this is why you'll hear them called distributed ledger technologies. Distributed, again, because everybody can see the ledger at the same time. Everybody has a consistent view of what's going on in it. But as I hinted before, blockchains get their properties from cryptography. So if you read Satoshi's paper, you'll see lots of references to cryptography. And what I'm going to do now is just take you through some of the basics of cryptography that is used in blockchain, so you get an idea of what mechanics go on behind the scenes when somebody talks about blockchains and why they're immutable and how they're decentralized and how you can assure that somebody that is paying somebody else, that there's incontrovertible that that person or that organization is the entity that authorized that payment. There's three concepts. Like I said, some of you might already be familiar with these, but I'm going to give it a kind of a light touch as I go through these. Hash functions, public key cryptography, and digital signatures, which build on public key cryptography. So let's start with hashes. Hashes are algorithms that create a shortened representation or digest of a larger piece of data. Typically, it's a fixed length digest that represents that data. And the characteristic of a good hash algorithm is that you can take a piece of data and modify it slightly and it will generate a completely different digest. And it's extremely difficult or close to impossible using current computing technologies to generate another piece of data that generates the same digest as a different piece of data. In other words, it's very difficult to create intentionally a collision of hashes. One way to think about a hash is to think about a summary for a movie like Star Wars, which if you summarize Star Wars, here's what a summary, one paragraph summary would look like, and there's no other movie that would have exactly this same summary, just based on the uniqueness of Star Wars. And by the way, we're all friends here, so let's just admit that the evil empire was, the empire was just trying to restore order to the universe. And by the way, the exhaust port will be patched on Tuesday. All right, that's an old Microsoft joke. But so let's take a look at a little bit more about the technical details behind what a cryptographic hash function like a SHA hash would look like, SHA-256 hash. You take the word fox, you hash it, you get the digest, you see a slightly different piece of text, hashes to something completely different, and the digest is the exact same length. You change just small, you change V to U, you get something completely different. You switch the order of the letters, you get something completely different. And that's the characteristics of a hash. You can uniquely identify any piece of data using its hash. And so the next concept I'll talk about is encryption. And I'll start with symmetric encryption, which everybody's familiar with. This is just you take an unencrypted message, you pass it through an encryption algorithm, which has a key that you apply to it, that key being unique, and then out pops an encrypted message. This, by the way, I've seen this kind of thing before when I've accidentally opened a Word document with Notepad, which I'm sure everybody, how many people have done that before? Yep, okay. Then you can take that piece of data and using that same key, decrypt it. And hence, it's symmetric cryptography. Same key can both decrypt or encrypt and decrypt. And those are very fast. And that's the kind of algorithms that would be used for, like, BitLocker, for example, to encrypt your hard disk contents. There's one key. It's used to encrypt the data. And when you go read the data, the same key is used to decrypt the data. Now, public key cryptography is really interesting because it's asymmetric. And so the same keys can't be used to encrypt as to decrypt. And the way that this works is you think of it as a lock. And that lock here has 3 positions. In the middle one, it's unlocked, like I'm showing here. If you take the public key, it can only turn the lock in one direction. And when you turn the lock in that direction, it moves to A, and that lock becomes locked. That public key cannot be used to turn it in the other direction, so it can't be used to take it from A back to B. The only key that can be used for that is the private key. The private key can turn it in the other direction. So the private key can be used to move from A to B, or from B to C, but it can't go back from C to B or B to A. And hence, the asymmetric nature of it. Now, it's called public-private key cryptography because these are generated as pairs together using prime factors, and they're paired together such that no other combination of numbers can lock or unlock the locks the same way that the public and private key can. Of course, the public key is something that the part of the key that you would give out to anybody. You could give it out to literally anybody, and the private key you would keep to yourself and keep it secret. You would hide it away so nobody else could have a copy of it. Once you've got this scheme in place where you've taken one part of the key and you said that's private and the other one's public, you can do some really cool things with that. One of the things you can do is encrypt data. And you can encrypt data so that only somebody else that it's intended to can receive it. And the way that you do that is you take a piece of data, you take the person's public key that you want to send this data to, and you encrypt it. So just like symmetric encryption, this key is used to encrypt the data, but once it's encrypted to that person's private key, nobody else with the public key can look at it. Even you cannot decrypt it using that person's public key that they shared with you. The only person that can decrypt it is the person that owns the private key. So they can take their private key and they can move the lock to the unlocked position on their side, decrypting that data. So it's a great way to, if you want to send a secret that nobody else can look at just besides the intended recipient, that's what you would do, is encrypt it with their public key. And if you take a look at what this looks like cryptographically, unencrypted message, encryption algorithm, receiver's public key, you get the encrypted message, you hand that to the receiver, now they can take their private key and decrypt it, and now they can read the message. Now, digital signing is something else you can do with public key cryptography, and this is heavily used in blockchains. If you want to prove that you're the person that did something, you can do that using your private key. And then other people can verify it using your public key, that you're the one that did something. And the way this works is just taking the lock in the opposite direction. You take the piece of data, you encrypt it with the private key, and then you hand it to somebody else, and they can decrypt it using your public key. Only people with the public key can decrypt it, and you know that if it's decrypted with somebody's public key, that they must have encrypted it with their private key. There's no other way anybody else could have produced that encrypted data because you're using that person's public key. That's the only key that will unlock that data. And so that is called signing. The way that you do signing actually is to take a message. You take this message here and you want to give it to somebody else and prove that you authorized this message. You said this message is the message that I want to give you. The way that you would do that is hash that message, so you get the digest, and then you encrypt that digest using your private key. So what you other person gets is the unencrypted version of the message, the encrypted digest of that message, and now they want to verify that you're the one, that message they received in unencrypted form is what you actually intended to give them. So the way they do that is they take your public key, they decrypt the message, they get back the hash, and then they compare the hash that was unencrypted with the hash of the plain text document that you shared with them. And if those match, that means that they actually digitally signed that hash, that document, effectively. Nobody else could forge that signature because nobody else has that person's private key that matches the public key that you used to unlock it. And so you just compare the two. If it's equal, you know that that's a verified message or authenticated message, a signed message. And those are the basic tools of public key cryptography that are used in blockchains. And now we've got the fundamental building blocks. We can start to talk about how we put these together to implement something like a cryptocurrency, like Bitcoin. The fundamental operation performed in a cryptocurrency or any blockchain is called a transaction. It's executing something, changing some state. In the case of cryptocurrency, that state is transferring assets from one account to another account. And in this case, we have Bob that wants to create a transaction in a cryptocurrency that's saying, pay Alice 10 of my Bitcoin. So the way that they do this is they take the ID of a previous transaction that shows that they received 10 Bitcoin. So their account in that previous transaction was assigned or transferred 10 Bitcoin. Now somebody can go back at that previous transaction, verify that Bob really owns 10 Bitcoin and the 10 Bitcoin that Bob is trying to pay to Alice. And then Bob would then, to give it to Alice and nobody else, would take and encrypt a transaction that includes Alice's public key and then sign it with his own private key. Now that this transaction is signed, it says that Bob authorizes the transfer of 10 Bitcoin from Bob's account to Alice. You can prove or verify that Bob actually authorized this by going and checking the digital signature with Bob's public key. And if the hash of the unencrypted transaction matches the encrypted hash there that was encrypted with Bob's private key, you know that this transaction is the one that Bob actually intended and put the stamp of approval on, give Alice these 10 Bitcoin. And so that's the fundamental way that a transaction is authorized. And why, when you're talking about cryptocurrencies, that keeping that private key secure is so important. If you lose that private key, then somebody else can masquerade as you. They can go on authorizing transactions that appear to be you because that private key represents something only you should be able to do. So once you've got this basic transaction, you start to build up transaction chains. And I kind of hinted at one before because I was talking about how Bob is referencing some previous transaction that shows that Bob owns 10 Bitcoin. So you see in a straightforward transfer of asset from one owner to another owner in this way, you can see there's one transaction here. Owner 0 signed this transaction that says give owner 1 some amount of currency. And owner 1 then can unlock that transaction and execute another transaction that says give this to owner 2. And the way that they unlock it, of course, is by digitally signing this transaction that they just created, saying give this asset now to owner 2. And then the chain continues like that. Owner 2 then can take and create another transaction, digitally sign it, and then somebody else, owner 3, can verify, and other people on the network can verify that owner 2 really transferred this asset to owner 3. So this is, you start to see this immutable kind of characteristic of blockchain show up here with these transactions that reference one another and have this immutable record of who authorized the transaction. In this case, owner 0 giving something to owner 1, giving something to owner 2. So these are the transaction chains that flow through a blockchain. Now, I haven't gotten to what a blockchain is. We're going to come back and look at that in a second, but I want to show you how you can explore transactions using, there's a bunch of different tools to go explore transactions on public blockchains. Oops. And I've got this site here. It's blockchain info, blockinfo.info. It's a great site for just exploring the Bitcoin blockchain. And you can see at the top of it, we see something called blocks. I'm going to talk about that later, but if you scroll down, you can see some interesting stats. So there's Bitcoin's value right now, 9,200. You can see the number of transactions a day. So this is the number of transactions that have been executed on the Bitcoin network in the last 24 hours. You can see here the market cap, 157 billion. And then what we're going to do is just click on this block. I'll explain what that is in a bit. But blocks contain transactions, and so we can go take a look at one of these transactions. And what we see in the transaction here are inputs and outputs. These inputs are the addresses of accounts in Bitcoin. And they're really crafted from the public keys of those accounts, those private public key pairs for that account. So when you go create a Bitcoin address, you're basically, and then advertising it to somebody, that's basically derived off the public key that matches the private key that you keep yourself to be able to execute transactions like this. In this case, the transaction has one input and it's got two outputs. And so what that is saying is that it's taking some input from a previous transaction and splitting it among two output accounts, and it's splitting it this way. So you can see the total input, total output matches in this case, and it doesn't always match. I'll talk about that later. And actually, it doesn't match. This is the difference right here, so I'll talk about that later. And that is the fundamentals of looking at a transaction. Underneath the hood, what you would see are references to previous transaction hashes signed here by that account, the private key of that account, the person that owns that account on the left side, that input account. You can have multiple inputs and multiple outputs. So I just happened to pick one that just had one input and multiple outputs, but you can have multiple inputs as well. So you can take currency from multiple accounts, basically combine it together, and then spread it out among multiple outputs. One little piece of trivia about a Bitcoin transaction is the input amounts have to match the output amounts. If there's a difference, that money goes to somebody called a miner, and I'll talk about that a little bit later. You can see the difference there, the fee, that goes to the miner. But there's no way to return unspent money to yourself. If you want to actually return, if you've got 10 Bitcoin in your account and you want to give somebody 7 and you want the change back, basically one of the outputs has to be back to yourself of the 3 Bitcoin difference. So that's what a transaction looks like. Now, we're ready to move on to the next building block in a blockchain and where it gets its actual name from, and that is the blocks themselves. And the way to explain where blocks come from, you got to talk about how the network agrees about transactions. So the challenge here with these networks and with transactions in this decentralized ledger is that the network is asynchronous. If they're sharing transactions with one another, we're all trying to keep track of what's going on. We can receive transactions in different orders. And you can imagine cases that are inadvertent or deliberate where Bob would say, I'm paying Alice 10 Bitcoin. And they sign that transaction and send it out to the network. And everybody gets this, Bob's giving Alice 10 Bitcoin. And then you can imagine that they also send out something else saying, using the same coin, I'm giving 10 Bitcoin to Joe. And now there's a transaction flowing around that has Bob giving 10 transactions to Joe. The order matters because one of those is going to fail. If you put the transaction to Alice first, then the transaction to Joe fails because there's no 10 Bitcoin in Bob's account. If you put them in the other order, the reverse thing happens. And so the network has to agree about what the order is, because everybody needs to know and agree about how much money Bob has, how much money Alice has, and how much money Joe has. And to achieve some common understanding, that's a process called consensus. And the challenge with consensus in these networks is that nobody trusts anybody. You might call this Thanksgiving in your house. But this is, nobody trusts anybody. In fact, there's people that are actually actively trying to game the system and double spend their coins. This is the double spending problem that these networks need to overcome. And so the solution to this double spending problem is to accept proposals for transactions from the network, from entities on the network that combine a bunch of transactions together and say, here's my proposal for the next batch of transactions that we're all going to add to the ledger and process. Now, the challenge to this is how do you determine whose proposal to take, and how do you stop the system from getting spammed with a bunch of just bogus proposals for transactions to be added to the ledger? The solution for that, in the case of Bitcoin, is something called mining. And this is, mining gets its name from the way that Bitcoin is actually generated. And I'll come to that in a second. The entities that try to collect transactions up and then submit to the network and say, hey, everybody, here's a bunch of transactions. Let's add these to the network, and here's the order that they're in. That's the mining process. And if you take a look at the mining process, they create these blocks with those transactions in them, and they link it onto the ledger in a specific place by having that block include the hash of the previous block. And then what that does is creates this immutable connection between one block and the previous block, because that block that was added has the hash of the previous block. And so you can see the network here, block 4561, block 4562, referencing hashes of basically everything that goes back to the beginning of time, because the hash of one block includes the hash of the previous block, which has the hash of the previous block, which has the hash of the previous block. In fact, you can think of it as the hash of the most current block has some information about the very first block on the whole network. You change anything in the middle, and everybody can tell something's screwed up because they can't follow that chain back. If I modify block 4561, that hash that's sitting there in block 4562 is not going to match that block, that unencrypted version of that block. So that's where we get the name blockchain, and also how we get this immutability. This immutability that shows the evidence that the entities that own assets are actually executing those transfers of assets, as well as the immutability of everything that has come before in the blockchain. So that's what miners are doing, is pooling up these transactions and submitting them. Now, it's called mining because they've basically got to dig for the win, the award that comes from actually producing this and having it accepted by the network. Because lots of entities are out there collecting transactions that are being submitted to this peer-to-peer network. They're putting them together, they're putting them in blocks, and then they're sending them out. And everybody else is trying to get a view of what the ledger looks like, so they get blocks from lots of different entities. And so, like I said, one of the goals is to try to prevent spamming of the network with bogus transaction blocks. So the way that the legitimacy or the genuine desire to participate in the network is established in the case of Bitcoin and many other cryptocurrencies is through something called proof of work. In proof of work, a miner has to show that they've invested something to produce this block that they're submitting to the network, that they've spent something, that it's cost them something, that they're invested in that thing being legitimately accepted by the rest of the network, because otherwise they're just wasting their money. And so the way they do that is by solving a cryptographic puzzle. I've talked about hashes before and how there's no way to, using current computing technologies, to generate a collision, meaning I'm going to generate this. There's a target hash I want to generate, so I'm going to produce some document that hashes to that. So that's why hashes are called one-way functions. I can't go from the hash back to a document. I can only go from the document to the hash. So the way that they prove that they've invested energy is they've got to produce a block that has a hash that meets a certain requirement, a hashing difficulty. So for example, we got to find a hash. We've got to generate a block that its hash with all of the data in it is below a certain value. Now think about that. Because the hash values, there's 256 bytes in a hash, that's a massive amount of space. How do I generate a hash below a certain value? I can't do it deterministically. I don't know what data to put in the block to do that. But the miners are given one little piece of data in the block format called a nonce that they can mess with to try to get the hash to come out to a specific target value or range of values. And so in the case of Bitcoin, what happens is the miners are given this puzzle and they'll have to find a way to generate a block with those transactions in it that they want to submit where the hash has a certain number of leading zeros. So you can take a look at right here. The only way to do that is through brute force, just to explore. Take that nonce and mess with it. And so you can see the nonce here goes from 0, 1, 2, you can see 4248, 4249, boom. 4250, we generate enough leading zeros, 4 leading zeros. At that point, we submit our block to the network and we say, look, we did the work to go find this nonce that makes the hash of this block have a certain number of leading zeros. And now the rest of the network can easily verify, yep, the hash of that block has a certain number of leading zeros. The only way you could have figured that out, because it's a one-way function, is to actually go brute force it. And so that's what miners do, is they brute force. They just search the space, randomly trying different values for the nonce. Before I come back to that, there's something else that can happen once, because you can have different miners that are producing legitimate blocks. They all are solving that puzzle in about the same time, plus or minus, probabilistically. And so the network, because it's asynchronous, different people on the network can get different blocks that are legitimate, that have that proof of work puzzle solved. And that's what's called a fork. So in this case, we have a fork here after block 234413. There were 2 legitimate blocks mined by different miners that both have the hashes of block 234413 in them. So the network at that point, if you're sitting on the network and you're keeping track of what's going on with it, you get one block, you add it on, you get the other block, you look at it, oh, this is legitimate too. You're not sure at that point which block the majority of the network is going to accept. So what you do is you just keep them both and then wait for the next block to show up. And the next block that shows up in this picture is block 234415 that points at 234414. And so what you would do is say, oh, this is the block that I think is the one that's going to win. So what I'm going to do, if you're a miner, is mine on top of that and try to create the next block that is on that part of the fork. The winner here is the longest chain. And the network basically converges on the longest chain over some period of time. Because of the probabilistic nature and the long delays in time it takes to generate a block, it's likely that one fork is going to start to grow longer than another fork by a long enough amount of time that everybody, even though the network is asynchronous, agrees on that view. So this is called the deeper chain. Chains are considered deep. So the deeper a transaction is in the chain, the more solid it is, the more likely it's not going to be undone. The risk of acting on a transaction, if it's not deep enough, is that the block that that transaction is in gets invalidated because that fork of the blockchain loses and the network agrees on a different branch. And what exactly is that risk? Well, if I, for example, accept a payment for a cup of coffee because I'm a store owner, and I accept that transaction, and the network then chooses a different fork than the one that block was in, the network doesn't recognize me having gotten that money. and that person that paid me that money might have paid it to somebody else. Now, it's unlikely that person's going to be malicious and try to double spend, but that's what the risk that could happen. The stakes are very high in cases where somebody might actually try to legitimately screw you. So if I'm selling a Van Gogh, for example, that's an expensive painting, and if I sell it for cryptocurrency, and I'm selling it to somebody I don't know, that person might really try to double spend. It's in their interest to double spend the money that they're giving me. And so what they might do is give me a transaction, give the network a transaction that gives me the money, and then immediately create another transaction that transfers the money to a different account, the same money, and hope that the branch that they gave me loses. And they use techniques like going and messing with the network to try to get this to happen. And if I give this person the Van Gogh, and then that branch that has the payment to me loses, I'm just out the money and the Van Gogh. So this is why the recommendation, when you accept a payment for some good, or looking at a transaction, that you don't consider it really solid until it's got some depth in the blockchain. And the rule of thumb for any decent sized transaction is 6 blocks, which in the blockchain network is about 60 minutes, because in the blockchain network, the goal for solving that cryptographic puzzle is 10 minutes. And what do I mean by how do they set this goal of 10 minutes? It's kind of interesting because the blockchain network, the code that it executes, it's watching how long it takes for blocks to show up that are legitimate blocks that have solved that cryptographic puzzle. And if blocks show up for a while significantly faster than 10 minutes, it raises the difficulty of that cryptographic puzzle. It says, oh, looks like the network's getting stronger. It's able to brute force more quickly. There's more miners out there brute forcing hashes, so I'm going to add one more zero to the puzzle and make it harder. That's why it's called difficulty. And if the network starts to slow down, these blocks show up more infrequently than 10 minutes, significantly for a while, then that means that there's less mining activity going on, fewer people are brute forcing, and so we're going to lower the difficulty of the puzzle to try to get it back to 10 minutes. So that's why you hear about Bitcoin transactions roughly, or blocks roughly be generated every 10 minutes or so. So you really want to wait about 60 minutes, and the chance of another fork coming along in the network that obviates that deep fork, that deep chain that you've already got your transaction in, is highly unlikely. There's so much work generated right now by mining that it's almost impossible for that scenario to legitimately show up, where you've got some miners off in the corner that are mining off a different chain to try to double spend and then obviate that transaction that you've got somewhere in the chain. So why do these miners do all this work? Why do they want to prove that they've got a stake by doing this proof of work? Well, they're rewarded for it. There's a transaction at the beginning of a block called the Coinbase transaction that they create, that the network agrees whoever mines a block that's accepted by the network gets a certain amount of coin, Bitcoin. This started at 50 Bitcoin in the Bitcoin network when it launched, and it halves roughly every 210,000 blocks. So every 210,000 blocks, the code that executes the Bitcoin network says, oh, time to only accept Coinbase transactions that are half of what they were before. And we're currently at 12.5 Bitcoin. So this is halving roughly every 3 to 4 years. You can see the Bitcoin money supply is going to run out sometime in the 2030s at this rate, at the rate that blocks are being generated. And that's intentional. Once the rewards through Coinbase are gone, the way that the miners are incented is through fees. And you saw the fees that were there paid by that transaction. Whoever executed that transaction said, I'm transferring money to this other account. I'm leaving some unspent. Any unspent money in a transaction that a miner mines goes to the miner. So that's effectively the way to give a fee, is to not spend everything that came on the input to the output. And right now the fees, you can saw it was a relatively small fee that was paid on top of that transaction, but as this Coinbase becomes more and more scarce, the fees are going to continue to go up. And that's the way that you're going to incent when you submit a transaction to the network, miners to take your transaction and add it to the blockchain. In fact, already today, the basic rule of thumb that miners follow, of course, is to be incentivized to put those transactions with higher fees into the blocks they mine, because that's more money for them. And so how they're doing this mining, by the way, this is a picture of my basement. No, actually, this is not a picture of my basement. My wires would never be a rat's nest like that. But here's a picture of my basement. So what you were looking at here are mining pools. So it's very difficult for you to now sit on one computer with a GPU even and successfully mine blocks, because there's so many other miners out there that are trying to generate blocks and doing proof of work at massive scale, like this in these farms of computers. That just do nothing but search for hashes, search for nonces that match the difficulty of the Bitcoin hash puzzle. These mining pools, the way they work, you can actually buy into them yourself. You go contribute to the money to the mining pool, and the mining pool is represented by basically an investment from everybody that's contributed money. If you contribute 10% of the money that goes into the mining pool, they're going to buy more mining gear. And if the mining pool wins a block, they distribute the coin base and the unspent fees to the members of the mining pool according to the percentage of their investments. So if I contributed 10% to a mining pool and my mining pool won a block, I get 10% of whatever fees and coin base came out of that block. And that's an incentive for people to all get together and have a higher probability of winning blocks. You know, you're going to get less money out of the block, but you get a higher chance of getting something than if you were just a loner going after it. You could win as yourself, but it's like winning the lottery at this point. Now, as far as who's doing mining, there's very few individual miners out there. It's almost all mining pools. 99.99% of Bitcoin is done by mining pools, and you can see here they can advertise who they are when they go and win a block. The reason that they advertise who they are, of course, is because they want you to go, oh, this is a winning mining pool. I'm going to go put money into that because then I'll have a chance of getting some return on the money that I put in the mining pool. The interesting thing about these mining pools is where they're located. You can see that China mining pools control more than 50% of Bitcoin's mining. And that's a potential concern to people. You've probably heard of the Sybil attack or 51% attacks on cryptocurrencies. With that much mining power, if they all got together and said, we're going to do double spending, they could do it, most likely. They could force the network to have big, deep chains that fork and have the people accept transactions on a long fork, keeping a longer one to themselves until they say, okay, now we've gotten all the Van Goghs in the world, let's go unleash the other fork that we've created that's longer. And now everybody's out of their Van Goghs and they still have all the money, all the cryptocurrency. Now, the disincentive to do this, of course, is that if somebody did that, the value of their currency would go to zero. But in the case of a miner that is saying, you know what, I'm going to just do one last thing before I'm out of here, and basically I cause this whole thing to come crashing down, but I'm walking away with a lot of Van Goghs, that's the potential risk. By the way, here's the other one, Slashpool. It's in Czech Republic. Now, also the interesting thing about China is that the Chinese government, the financial regulators there, have banned cryptocurrency. And this is from about 2 months ago. Game over, China wants an orderly exit. Basically, they said, we're banning cryptocurrency. In fact, we're also banning mining. You can't do mining anymore. Now, I've tried to look and see what's going on with this, but it's still, that mining chart is from yesterday, so the miners are obviously still hard at work mining. And so it's not unclear at this point what's going to happen to those Chinese miners. What I really think is going to happen to those Chinese miners is they'll just go offshore with their mining operations. But it's going to be interesting to watch this play out, given all this mining power in China with the Chinese government saying they don't like cryptocurrency or mining. Now, speaking of all that mining power, we've got a potential problem here. It's what's considered an environmental catastrophe. If you consider the amount of compute power that's thrown at mining Bitcoin at this point in time, an individual transaction, right? So only one miner wins, and the amount of energy they spend on just mining that winning block is relatively small. But all of the energy everybody's spending trying to get that winning block all adds up, such that an individual transaction, when you clear it on the Bitcoin network, when you submit a transaction to give somebody else some of your Bitcoin, is about 270 kilowatts of power has been burned for getting that transaction onto the blockchain. The total amount of energy now consumed by the Bitcoin network is about the amount of energy the country of Denmark consumes. So this is why there's a lot of people that are concerned about how much energy is being spent just solving this cryptographic puzzle for these cryptocurrencies. Now let's go take a quick look at blocks before we move on. So we were here in this transaction, and you can see that it's included in this block right here. In this block, it has a bunch of information that's embedded inside of it, like the number of transactions are in it. You can see the total output of all those transactions is this amount of Bitcoin, which is the estimated transaction volume is 317 Bitcoin. So that's the amount per transaction, roughly, that people have spent in transactions on this. You can see the difficulty, so that's effectively the number of leading zeros that the miners have to hash. And if you scroll down, you can see all the individual transactions, what we were seeing before. So you can see most of them are, here's 2 inputs to 1 output. Here's 1 input to many outputs. So somebody's splitting up a bunch of coin and sending it off in different directions. So that's a quick look at blocks. And of course, you can take this and you can say, well, here's the hash of this block. Here's the hash of the previous block. And we can follow this chain all the way back to the beginning of time, or the Genesis block that Satoshi Nakamoto made. So that's a quick look at the blockchain for Bitcoin. If you put this all together, the Bitcoin network, so there's different kinds of nodes on the network. The ones that are keeping track of the full state of Bitcoin, they're called full Bitcoin nodes. There's about 10,000 of those, and that's really what determines what's on the ledger, what's in Bitcoin. There's all these nodes agreeing this is the way the Bitcoin's all divided. According to these rules that we all agree on, the most work wins. And anyone can spend transactions. You can go buy it. You typically buy it from somebody that owns Bitcoin, give them fiat currency in exchange for it. You get now your own account that you created. You tell them to send it to. And once it's there, you can then go and send Bitcoin to other people on the network. There's a bunch of other cryptocurrencies that have evolved over time that are very popular and also have decent market caps. Litecoin's one. Ripple XRP's another one. How many people have heard of Ripple? I'll come back and talk about that one right now. The Ripple is one that's got the cryptocurrency purist a little upset because the way that I describe Bitcoin, there's no central authority. The money is created through mining, so nobody controls who gets it. Nobody controls the amount except for the algorithms themselves. In the case of Ripple, or XRP, there's a company called Ripple that actually issues this currency. And the way that they've generated it is they've given a bunch to themselves. And so you can see this is not a decentralized cryptocurrency. It is a cryptocurrency, but it's not decentralized. It's based on blockchain. Everybody's got a common view of what's going on, but given the cryptographic keys to the network, only the Ripple founders can go generate more XRP. So it's not mined in the traditional sense, or at least the mining doesn't account for all the XRP that they can inject into the network. And so this puts them among the richest people in the world. Now, Ripple prices have come down since this article came out. At the time this article came out, they were worth, get this, $60 billion. So that's kind of money that's going into cryptocurrency. And then here's another one, Ethereum. This is another public cryptocurrency network. This one has a decent market cap as well. It's up in the tens of billions of dollars. But this network isn't designed to be a cryptocurrency network. It's designed to be a network for what are called smart contracts. So let's talk a little bit about smart contracts. This is extending the blockchain not just to have simple transactions of asset transfers from one account to another one, but actually to store programs. And those programs can be used to encode business problems. Basically, you can encode contracts as code itself on the network. So they're called smart contracts because they basically execute on their own. Nobody's in control of executing them. You can send events to them. You can call functions in them. The network executes them. In the case of Ethereum, is an Ethereum virtual machine. The language to write these small contracts is called Solidity. I'm going to show you an example of that in a minute. And you can, basically, it's Turing complete, so you can write very complicated contracts inside of Solidity and run them in the public blockchain on Ethereum. And again, every state transition is logged into the blockchain, the Ethereum blockchain, so it's immutable. So you can go back and follow the execution of a smart contract back to the beginning. If you take a look at what a smart contract looks like, I'm going to show you this in a second, but it's got some characteristics here. You can hold or transfer on-chain assets, meaning you can even have smart contracts can own Ether, the cryptocurrency of Ethereum. They can send Ether to other accounts. They can receive Ether, but they can also generate their own forms of currency on top, and that's something that people have been doing that I'll talk about in a minute. There's some big challenges to writing one of these smart contracts, because once you put it on the ledger, it's there, and you can't change it. And if you have a bug in it, you're in trouble. There's been a high-profile case of the DAO, a distributed autonomous organization. Back in the middle of last year, they had a bug in their smart contract that allowed somebody to go and call it recursively and empty it of the Ether that was assigned to that smart contract and give it to themselves. And they gave themselves tens of millions of dollars before this thing was shut down. And what that caused is the great Ethereum fork of August of 2017, where the Ethereum founders and committers were faced with this conundrum. The DAO had lost huge amounts of money through this bug in their smart contract. So the question was, oh, well, they screwed up. Let's just continue because this is a decentralized currency. We shouldn't be the police for this. If people screw up, they screw up. And then there was the other faction that said, no, no, no. If this can happen like this for huge amounts of money like that, then that's going to undermine people's trust in this network. And they're not unwilling to invest in it because their risk of losing something like that to a bug like that is too high. So, you know what, let's go fix this. And so what they did was fork Ethereum. At a certain block, they said, we're going off in a different direction from the main network, and this direction is going to give the money back. We're all going to agree this money goes back out of that account into this account, into the DAO account. And so there was a rift, and there were two Ethereum forks that are now out there. And the Ethereum that I'm talking about here is the main net, the one that forked, the one that gave the money back to the DAO. That's the one that's got about 5 times the market capitalization of the other one. By the way, Bitcoin is also forked into 2 different Bitcoin Cash and Bitcoin, BTC and BTH. And it's forked because of differences in opinion between the people writing the code for the network. There was one faction that said, we want to make the network execute faster and have larger blocks of transactions. So and another group that said, no, we're not ready for that. So they forked. Now, Bitcoin was the side that didn't change the algorithms. Bitcoin Cash is the one that did, and now that's about 1/5 the market cap of the main Bitcoin. So let's take a look at a smart contract business process. You have a buyer, you have an escrow agent, you have a seller, and the business process is the buyer gives money to the escrow agent, and when everything's approved about the sale of the house, then Bob gives Alice the house, effectively. The title's transferred. Now, you can encode that business process into a smart contract where the escrow, basically, if Bob, Alice, and Eve, the escrow agent, agree that they return the money back to Alice. If Bob and Eve agree, they pay the money to Bob, and otherwise, they split the money between Alice and Bob in the case there's a dispute. So the escrow agent here is in the middle. A dispute resolution is encoded in the smart contract, a dispute between the buyer and the seller, where the buyer has already given the money to the escrow agent. And we can resolve that sitting right here in the smart contract, encoding it in code, and then executing functions to cause the state transition here to say, signal basically Bob agrees. And the way that Bob can prove that he agrees is by signing a transaction that says he agrees. And that transaction is a call into the smart contract. And that changes the state of the smart contract to Bob agrees. And then Alice can choose to say, I agree or don't agree. She can sign a transaction that indicates her choice. And that way, that kicks off the next step in the transaction in the smart contract, which is to say, OK, they don't agree. So if Alice and Bob agree, I guess that don't agree is not in there, then we've got the escrow agent in the middle to kind of resolve the dispute, and they'll either pick Alice or Bob, and the money will go one way or another. So that's just a very simple example of a business process that's encoded in a smart contract. Now, there's other kind of more frivolous processes that are encoded into smart contracts on the Ethereum network. How many people have heard of CryptoKitties? So quite a few of you. If you can go to that URL right there, you can buy yourself a kitten. Now, this kitten exists only in the Ethereum blockchain, and it's randomly generated kitten. So there's like 1,024 characteristics or genes that these CryptoKitties have. They're randomly generated, and what happens is, depending on your genes that you get randomly generated, you get a different looking CryptoKitty with different characteristics, different colors, different eyes, different tails. And what's happened is that people have decided these things are really cool, and they're starting to collect them. In fact, somebody actually spent $100,000 for a CryptoKitty. So you can have your cool-looking CryptoKitty, you can offer to sell it to somebody, and then get Ether that then you can transfer into real cash. And so somebody has spent $100,000 of Ether to get somebody else's CryptoKitty that they thought was really cool. Over $20 million have been spent buying CryptoKitties. So this is an interesting phenomenon. Now, the other thing you'll see on smart contracts are initial coin offerings. So I've talked about Bitcoin, Ethereum, but both are platforms that you can use to launch other currencies on top of them. And this is called an ICO. How many people saw Silicon Valley this Sunday, by the way, the show, HBO show? So if you haven't seen it, Pied Piper, the fictitious company there that we love because they're an Azure customer, they launched an ICO, Pied Piper coin. So everybody's getting into it, and you can see the amount. This initial coin offering is like, a public sale. I'm going to create a new token, and when you can sell the token then for the cryptocurrency that you want. So Ether or Bitcoin, whatever network it's on, and people can buy coin from you, and then you get the money. And you can see that this is the way now a lot of companies are raising money, is through these ICOs. Over $4 billion has been raised. Regulators are like, wait a minute, this is like an initial public offering of stock sale, but it's done on cryptocurrencies, on this blockchain that's decentralized, nobody has control of it, and so rules around it are still vague. Let me now take you into Ethereum smart contracts. And what I want to do to demonstrate these Ethereum smart contracts is today I'm going to launch Mark's token. I'm going to do an ICO today that I hope you all buy. No, actually, I'm not really launching an ICO today, but I'm showing you what it would look like and how easy it is for you to do your own ICO. This here is an editor here. It's Visual Studio, and it's got the Solidity plugin for it. And this is a smart contract I've got here loaded in Visual Studio. It's Mark's token's contract. And I'm going to show you some of the code in here. We've got some safe math. That safe math, necessary in any smart contract that does math to prevent overflow and underflow, because if you do that and you're playing with cryptocurrency, you can really screw yourself. So you want to use safe math functions. And then you can see I've got something here defined as an interface. This is the ERC20 interface. This interface is the standardized interface for tokens built on top of the Ethereum blockchain. So any ICO on the Ethereum blockchain is going to implement these interfaces, and that allows tools, like we're going to see in a minute, be able to look at the tokens that are implemented by this smart contract that I've got here. You can see that there's functions like what's the total supply of the coin, the token. I can call a function like transfer is to take some of my token and give it to somebody else. And the way that an ICO works is that there's a function called a fallback function. If somebody sends money to a cryptocurrency, that money, or that cryptocurrency, sorry, somebody sends cryptocurrency to a smart contract, it gets routed to a function called fallback that determines what happens to that money. Where's my fallback function? Here it is. And if you want the smart contract to receive money, you do this, payable. And so that's what it is. And what all this fallback function is transfer money into the owner, smart contract owner's account. The smart contract owner is by default the account that submitted the transaction to publish that smart contract on the blockchain. You can see I've got a constructor up here too, which kind of defines the symbol, the name, the units 1 Ether can buy. So if somebody gives this smart contract 10 Ether, they get back 10 Marks tokens. And then the total supply, I've made quite a big supply for myself, because I expect to raise a ton of money. And then what I can do here in a local dev environment, truffle dev, is compile that code. First I'm going to delete the previous output, and I can type compile, and then what I can do is type migrate, and that will deploy it in my local system in a synthetic blockchain here I use for debugging purposes, and then I can do things like Marks token deployed, and then I can put in a lambda, return I dot total supply, just to show what the total supply of my coin is. Yep. All right, what did I do? Unexpected token. Oh. That goes there. Oh, that goes, oh, sorry, it's on the wrong side. There we go. Nope, all right. What did I do wrong then? All right. It's going to take me too long to figure out what typo I had there. But basically what I can do is right there inside of this little debugger is I can interact with my smart contract. Now what I also can do with that smart contract is publish it. And so I'm going to publish this smart contract as an initial coin offering, not in the main Ethereum network, but in a test network called Ropstein. This is an IDE called Remix. I've got my same smart contract up here. And if I say run, I've already run deploy, what that's going to do is ask for some test ether, and then deploy this to this test network, Ropstein. And actually, I've already deployed this previously, a version of this contract. You can see it's here. And you can see the smart contract address. It gets its own address on the network. It looks like any other account address. It's got a private key and a public key. You can see the transactions that this smart contract's accepted. What I've done already with this version of Marks token is transfer money into it and out of it between parties. And because it's the ERC20 interface, these UXs like this know it's a token. And you can go click on the token, and then it will show you things like, oh, these are all the token transfers that were made of Marks token. And here are the token holders. So that's an example of smart contract as a cryptocurrency, as a token deployed on the test Ethereum network. And now if I wanted to do a real ICO, I could go and launch that on the main Ethereum network and then say, everybody, hey, go buy some Marks token. You're going to get rich. I'm going to get rich. We're all going to get rich together. It's going to be awesome. Now, the smart contracts, I showed you some frivolous cases, ICOs, kind of raise money, as well as cryptocurrencies, kind of beanie baby thing. But blockchains and smart contracts are used in many enterprise scenarios and useful for them. If you think about them in trade finance, to do cross-border payments without any middlemen, without any settlement fees, without any settlement delays of transactions from one company to another one. You can think digital music rights. Who owns the rights to this piece of music? If that was on a blockchain, everybody could know which artist to pay or which organization that owns that rights to that they should pay whenever they play that song. Today, artists get very little of the money that they're actually due because nobody knows who they should pay, what account they should give money to when they pay music. Diamond tracking is another one. So the legitimacy of diamonds. So if you've got a diamond, it's got a certificate of authenticity with it from a company you trust, and you can go look at the blockchain and see that this actually diamond came from that company and was actually sourced from a legitimate place. Real estate sales. So this is where you're transferring assets from one house to another, or from one person to another. I kind of showed you a shortened example of that back with the escrow thing. Supply chain management is a huge scenario for enterprise blockchain. Keeping track of what suppliers have and where things are along the supply chain when there's multiple suppliers and the goods being shipped between them. Today, if you take a look at the hotel business, which is a hotel supply chain problem with a lot of hotel operators having inventory that they're selling to purchasers, right now there's about $10 billion a year in fraud in the hotel industry because of the lack of the decentralized view of what the hotel inventory is and who owns it. Again, when somebody sells their hotel inventory to somebody else, then things can get double spent intentionally because of fraud, and things can get lost as well because we just lose track of who has it, who has that inventory, which can happen if we're maintaining our own views and our own databases of what's going on. And the list of potential scenarios is really limitless. We've got one in Microsoft that we're creating. It's a consortium blockchain, meaning only certain parties can participate in the blockchain. They're authorized to participate in it, as opposed to the public blockchains that I've been talking about. This is the Microsoft Treasury working with Bank of America to do standby letters of credit on behalf of purchasers, or the partners that we've got. And we work with the Bank of America to issue these standby letters of credit for them, or we get them from Microsoft to the applicant. You can see the complex business flow that is simplified if we encode this on a smart contract and just have this execute on the smart contract where the partner, where us, and where Bank of America can all see what's going on at every step of the way. And the rules are encoded in the smart contract so they execute in an automatic manner. So we're seeing lots of interest, and Ethereum is just one of the potential networks to run these kinds of smart contracts. You can see some other ones. Corda, Hyperledger Fabric, and Quorum are other examples. But one of the challenges with many of these is that they work on proof of work or other consensus algorithms that waste energy or have low performance in transaction clearing or throughput, and they lack governance. And this is where we've created something called the COCO Framework, which is based off of something called the Trusted Execution Environment. If you were in my session this morning, you saw what that is. It's basically a black box on a processor, and you can use these to establish a trusted network where we all trust the code, we all trust the blockchain code, we all trust it to do what we expect it to do, and then it can implement rules that we agree to, and it can establish consensus very quickly because every node trusts every other node and every participant in the network trusts it. So I'm going to show you a really quick demo of public Ethereum versus a COCO-enabled Ethereum executing 2,000 transactions that have been recorded off the public Ethereum network. You can see that the COCO network has actually just completed them all. And it's executed at about 1,600 transactions per second. You can see the average latency is 5 seconds. Actually, it should be less than that. There's something wrong with the UX. All right. Typically, what we see is 1,600 transactions per second. And you can see the Ethereum side. The Ethereum proof of work is 10 seconds rather than 10 minutes like Bitcoin. But that means you got to wait about a minute before you can trust a transaction is clearing on the public Ethereum network or a consortium network that's using the public Ethereum proof of work consensus algorithm. So finally, just want to let you know that you can get started by creating a wallet. Coinbase is one of the popular places to get a wallet. You can download Bitcoin and set up a full node. You can join a mining pool if you want to. Warning about these exchanges. So Coinbase, well, that's not a warning, but Coinbase is generating a huge amount of money just because all the people that are going and signing up and buying cryptocurrencies through them, $1 billion. But this is something that can happen. It's happened to several exchanges, is that they get hacked and the money leaves. So these are basically like banks with the amount of money that they store and the amount of money that attackers want to go try to get into. So finally, some resources to point you at. Blockchain on Azure. One of the things to check out if you're interested in enterprise blockchain scenarios is Workbench, which we released this week at Build, which simplifies everything you saw there. You're not sitting in low-level tools like that to create smart contracts or interact with them. You're sitting in web UXs that are deeply integrated with Azure services for enterprise-grade key management and authentication and UX to understand what the smart contract state looks like. It's really something I think we're going to transform enterprise blockchain just by making it so simple. So there's a place to go sign up. And there's actually a GitHub repo where you can go check out a whole ton of samples for Workbench. And here we got it over here. So go check out the Azure samples for blockchain. And that brings me to the conclusion of the talk. I've just got one last thing to show you. And one of the challenges with Bitcoin, or values of blockchains, is that they're immutable, which is also one of the risks or maybe benefits of blockchain, depending on how you look at it. This is a transaction here you can see on the Bitcoin Cash Network. It's got one input and lots of outputs. This is actually encoding an image inside of these outputs, which are not real Bitcoin Cash addresses. They're just there encoding bits in a PNG file. And this is the PNG file that's going to be forever on the Bitcoin Cash Network. So with that, I want to thank you very much. Good luck with cryptocurrency and smart contracts.